All right, hi guys, and welcome to Coders Campus. This is going to be an assignment walkthrough video for one of the students inside of Coders Campus. If you are not familiar with Coders Campus, you can go and check it out at coderscampus.com. It's just a little community that we have where for programmers where you can actually get help with your assignments, homework, prep for exams, interviews, questions and answers, mock interviews, and so on and so forth. So this particular person was given an assignment. They had to create the implementation of a linked list in Java. So a linked list in Java is essentially a bunch of nodes that are all linked together via a pointer to the next node. Okay, so I'll show you exactly what I'm talking about, but first I want to start things off by sort of creating a package. So I'm going to create a new package, which is, where to go, package, there we go, and I'll just call this linked list, and I'm going to go inside my package, and I'm going to create a new class, and I'll call this my linked list, because I don't think I can call it a linked list because that word is reserved via Java. It has its own linked list implementation, so we don't want to use the same name. So there we go. And it will create my file. So now what's going to happen here is we want to create a list of nodes. So essentially there's going to be a bunch of nodes that all hold pointers to the next node in the list. Okay? And each node contains some sort of data. Okay, there's a reason why we're storing these nodes and pointing them to each other. It's because they have some sort of important data within the actual node itself. Okay, so in this case, I mean generally when it comes to 101 level programming assignments like this, usually the data it holds is like integers, just numbers. But that data can really be variable. It can really be strings. It can be characters. It can be objects. It could be whatever you like. How I'm going to implement this is just with integers, but you could very well substitute object if you like and have it store just a generic object, or even using Java templates and use templating, but that's sort of outside the scope of this person's particular assignment. So here is what we want to do. We want to create this structure, and we want to also have it be able to add a node, as well as delete a node, and find a node. Okay, so those will be the important aspects of our data structure that we're going to be creating. So first thing is first, what I'm going to do is, since I've talked about these nodes, we need to create an object to represent the node. Okay, so I'm going to do that inside of my linked list package. I'm going to say new class. I'm going to call it a node. Say OK. And so now we're looking at this node. So like I said, back here, we have nodes that store data and pointers to the next node. Okay, data and pointers to the next node. So how do we represent that in terms of a Java class? Well, the data is easy because you could just say int data, and that is going to be the data that this particular node stores. And that is a good way to think about it, what I just said there. When we're looking at this class code, this is going to be the code that represents a particular node. Okay, so for this particular node, this is the data that exists inside of this particular node. Okay, so now what else do we need to have? We need to have a pointer to the next node. So this particular node needs to have a pointer to the next node. How do we do that? Well, we can do something sort of like a recursive thing here. We create another node, which is data inside of this particular node, or rather a pointer, and we can call it next. Okay, or next node, whatever you want to call it is fine. So there we go. That's essentially the structure of this particular node. And then we want to obviously create our getters and setters, which are used to get and set the data and the next node variables. So I do that by hitting Alt-Shift-S. That brings up this menu. And then I hit R, which actually is, where is it? Generate getters and setters. You see my R here is underlined. So I hit R, and that generates my getters and setters. I can select data next node and say OK. And boom, it creates that getter and setter information for me. So there we go. That's essentially going to be the makeup of my node class. Fairly straightforward. So now let's go back to my linked list. And I want to start actually implementing some of this code. So essentially we've done the first part, which was to establish the structure of the node class. And now we need to do things like adding a node. So let's create that now. We'll create a public class. I don't think this class needs to return anything because we're just adding a node, so there's not really anything to return. So we'll just say void. So instead of returning something, we'll say void. And we'll call this add. Okay. Now, what do we need to know in terms of adding something into a linked list? When we add a node, we need to actually have a node to add, right? This is the node that we want to add to our list. So what else do we need to have? Well, we need to know that there is a start to the actual linked list itself, right? There's a sort of like a root node. In a linked list, this is known as a head, okay, the head of a list. So we can actually define this as being a node, because again, the head, which is right here, okay, if I want to create, something that sort of points to the node, this is our head, right? I'm not sure if I can create a character that points down. In any case, this is the head of the linked list. And therefore, since we have a reference to the head, we may also need a reference to the end of the list, which is the tail, okay, which is the last node in the list. Okay, so head and tail. So that's important to know because now we've created an actual head for the linked list itself. Because remember, when we create a linked list, the linked list needs a head. Okay, each individual node doesn't need a head, just the linked list, which is why I created this head variable inside the linked list and not inside of the node class. Okay, important to understand. So now we need to be able to add a node into our linked list. So now let's think about it. There are situations or scenarios that can unfold here. So scenario 1 is we have an empty linked list. Okay. Scenario 2 is we have a non-empty linked list. Okay. So those are two important scenarios to think about when we're adding a node. Okay. So let me handle scenario 2. We have a non-empty linked list, which is probably the code that you'd want to write naturally first. You'd want to say something like, okay, when we add a node, we want to add a node to the end of the list. Okay, so obviously, if I want to add a node to the end of the list, I need to add a node probably to the tail, right? So we have a tail here, and when we want to add a node, we need to add it to the end of the list. So that leads me to believe that we also need to define a tail. Okay, so if we have a non-empty linked list, that means that tail has a value. Okay, so for example, a non-empty linked list could be like this. We have a node that has data 15, which points to the next node, which has data, 16. And that is essentially our linked list. Okay, so this node 16 would be the tail. So tail would point to node 16. So now what we would do is, let's say we want to add node 17 into the list. How would we do it? What would that look like after we add the node? Well, it would look like this. We'd have node 15, and then we would have node 16, and then we would have node 17 because we're adding it to the end. Now, I just realized I'm using sequential numbers here, which might lead you to believe that it has to be a sorted list. So I'm going to change this node. I want to change it to be 10 just to show that it's not actually a sorted list. So that would change to 10 as well because we want to add the 10 to the end of our linked list. Okay, so how do we do this? What is it that we need to do to accomplish this particular task? Well, there's a few things. Look at what happens. Node 16 points to node 10. So that means that the old tail needs to point to our new node, and we need to update our tail to point to our new node. All right, so essentially what we're doing here is we're saying tail dot next node. Okay, although I should probably say get next node, or rather set next node. And I'm wondering now if it makes sense to have these whatchamacallits, the getters and setters in this case. It depends on how your professor would want you to implement it. I'm gonna actually go ahead and get rid of those declarations for the getters and setters, and I'm just gonna leave this defined like it is, because right now these are defined as package level. So if you don't have a modifier in front of the int here, like if I had said private, then it would be obviously private. If I have it set as public, it'll be public. If I have it set as nothing, then it'll be package level, which means that everything inside the linked list package will be able to access this data. So I'm going to leave that as is, and it's package level. Therefore, since my linked list is inside of the linked list package, I'll be able to reference next node. Okay, let me just double check that. Tail.nextNode, yes. So then I want to say tail.nextNode is equal to the new node that we're adding in. Okay, because remember, the tail, or rather the current tail, which is here, node 16, which is what we're referring to when we say tail here. So we say tail, which is node 16. The next node, which probably was previously empty because it's not pointing to anything, is now pointing to node, which is the new node that we're passing in, which is node 10. All right, so that sort of satisfies this. So now we'll have this structure, but the tail will still be pointing to node 16, which in this case is here, and so that's not good. We want to update that. So now we want to say tail equals node. All right, does that make sense? Tail.nextNode. So that was the existing one, and then we're updating the tail. So that's essentially scenario 2, and we can certainly test this. We'll see. It's been a while since I've implemented a linked list, so I'm not exactly sure if this is correct, but we will absolutely go through and debug. But the scenario we haven't tackled is number 1, where we have an empty linked list. So what happens if we have an empty linked list is that tail is null, and this will give a null pointer exception, which is obviously bad. So we need to do a check, and we need to say if tail equals null, we need to do something. Otherwise, this is what we need to do. Okay, so that's kind of scenario 1, scenario 2. Scenario 1 here, scenario 2 here. So if the tail is null, so if we have nothing in our list, that's actually then pretty simple, because all we need to say is tail equals node. Does that make sense? We have nothing in our list, therefore, as soon as we add something into our list, then we will have the tail pointing to node. Now, I'll probably get ahead of myself here and say if there is no tail element, then there's also no head element. So we probably also want to assign the head to be node as well. All right. So that means if there's one element in the list, it is both the head and the tail of the list. So we're going to do that. So there we go. That is essentially how I would do this first little example. So now, of course, we need to test our code, right? Oops. So how do we test our code? Well, you can do it in a bunch of different ways. What I'm going to do is I'm going to create a new class. I'm going to create a new linked list test class. And I'm actually going to go ahead and create a test annotation. If you haven't seen this before, then let's not worry about it. But essentially what we can do is we can set this up so that it uses something called JUnit to actually run the code. You might be familiar with the public static void main method to run your code, but I'm just going to use this test method just because I'm used to using test methods. So I'm going to create this method, and I'm going to instantiate a new myLinkedList, call it a list, equals new myLinkedList. Okay, so now I'm writing the code to actually test my stuff here, and I want to say list.add, and I need to create a new node to add. Now I see I want to add a node like this using this notation just because it's easier, but there's no data inside of this node, so I want to create a constructor inside of the node class that allows me to pass in data. All right, so I'm going to create a new constructor. I'm going to say node, and I'm going to just double click on the default constructor here, and I'm going to add another parameter where I pass in data. So I say this data equals data. So whenever someone passes in data via constructor, it will take this data here, this is the variable, and set it to be equal to the instance variable, which is here for the actual node class. So that'll actually set my data. So now I can say node, what did I say, 15? What was my example? Yeah, 15, 16, 10. So I'm going to say add new node 15. Then I'm going to say add new node 16. Then I'm going to say add new node 10. And then I'm going to actually, let's see, how can I do this? I'm going to, I want to iterate through the list now to verify the contents. Or maybe that's getting ahead of myself. Maybe I will just add a system out line that says done. And I'll put a breakpoint here on this system out line so that I can actually verify the contents of the list. So that's what I'll do. So let me go and right click here, and I'm going to say debug as JUnit test. So this is actually going to run my code that I just wrote as a test and in debug mode. So I'm going to say it wants me to switch perspective, so I'll say yes to switch to this new perspective. And okay, so we've hit this point now. We've run through our code and we've hit this line without any error, so that's good. Now I'm going to hover over list and I'm going to see what is actually in the list. So, oops, let's see what's in our linked list. So what do we have here? We have a head and a tail. The head is 15, which is good. We want it to be 15. Our next node is 16, and then our next node is 10, and the tail is set to 10. So that's perfect. That's exactly what we want. We have a head set as 15, we have a tail set as 10, and we have a bunch of next nodes that point to 16 and then 10, and the last node doesn't have a pointer to the next node at all. So it looks like our adding function is working just as expected, so that's great. Let me switch back views now and to our regular view. So now what I want to do is I want to create the next function, which is the delete node function. So how does this work? Public. Now usually I wouldn't say void delete, because what I would probably want to do here is I probably want to return the node that I did just delete. So this is usually sort of the way this code works in terms of regular linked lists. So I will assume that your assignment wants you to do the same thing to actually return a node. So now when I have this new node that I want to return, I need to think about what a delete does. So what are scenarios for deleting? Well, scenario 1 is an empty linked list. What do you do in that case? Scenario 2 is we have a obviously non-empty linked list. Those are important. Excuse me. So are there any other scenarios that are important when you're thinking about deleting a node? And off the top of my head right now, I can't think of one, so fair enough. One thing I missed here is, what am I doing when I delete? Usually when you're deleting a node, you want to say what node you want to delete. Just like I said up here what node I want to add, I'm saying down here what node I want to delete. So what should happen? Well, let's think about it. Let's say we have this scenario here, and we want to delete node, let's say 10. What do I need to do to delete node 10? Well, here's where we're going to get a little bit fancy, because what we need to do to delete node 10 is we probably need to go through the list and find node 10 first, right? So you'd search, you'd say, okay, here's node 10, I need to find it. Is this node 10? No. Is this next one node 10? No. Is this one node 10? Yes. Delete it. And then we need to do some stuff. So really, we need to first implement find node 10 before we can actually delete it, right? So let's pause what code we had there and go on to the find function. So let's do that one first. Public node find node. Now, let me think about this. Do I need to return the node that we just found? Probably not, because we're passing it in. Although, does it make sense to find by node or find by data? I'm thinking that it makes more sense to find by the data itself, which means it might make sense to return the whole node. Just like delete, actually, now that I think about it, you'd probably want to delete based on data and add based on data, not based on node, right? Because we don't want to add a node. We don't want to have people have to understand what a node is in order to delete the data. All they care about is the data itself. So let me go back now and modify my add to say, with this new information here. So I want to say node equals new node with data. Okay, so that's what we're going to do. We're going to create a new node within this add method based on the data that is passed in, and then we're going to add it to our list. Okay, so that's how I would sort of change things there. Doesn't change too much, but other than the concept of how people outside of the linked list would use it. Because now if I jump outside, you see here that I'm not adding a new node. What I can do is I can just say add 15, add 16, and add 10. Okay, much easier than add new node, new node, new node. See what I mean? So let's go back to our linked list. Let's go back to our find, and let's implement the find method. So this one's fairly straightforward. We need to just sort of go through the list and see and do a comparison to see if we have the node that we want or not. So the same sort of situation exists here, an empty linked list versus a non-empty. So we can say if head equals null, we return null, because that means that there's nothing in the list. If there's no head to the list, then there's nothing in the list, so we can return null, meaning we haven't found anything. Otherwise, we need to iterate through the list. So essentially what we need to say is while head.nextNode is not equal to null, we can actually iterate through this list. Okay? Because we know head is not equal to null, so we know head has a value. And we can say, let's see, while head.nextNode. So I guess we need to do one more check here. We need to say if head is equal to, or head.data is equal to data, which is what we're passing in, then we return the head. So we need to make sure that we check to see if the head is indeed a match with the data or not. Otherwise, then we can start iterating through the list. So we can say, well, head.nextNode is not equal to null. We can say, let's see. Oh, we also need to be iterating through the list. So we can say node equals head. So maybe that's what we can do. Node.nextNode is not equal to null. And then maybe we can do that check that we were just talking about. Does that make sense? Maybe not. I just want to make sure I cover all my bases here. Well, next node is equal to null. I can say if. No. I can say node equals next node. Sorry. Node.nextNode. And then I can say if node.data is equal to data, then I return this node. All right. So, and then I can say return null if it wasn't found. So, see what's going on here? Sorry, I didn't really explain myself as I was going through here. So, the first obviously important step is we need to make sure that if the head is null, if we have an empty list, then we return nothing. This is check the first element for a match. So that's important to do. And then we assign node as the iterator, essentially. So the node is what we're going to use to iterate through the list. And then here we will iterate through our linked list. So we'll say while the next node is not equal to null, so while we have a next node to sort of iterate towards, then we iterate towards it. So we say node is equal to the next node. So now node will be equal to the next node in the list. And we know that the next node in the list exists because we've done a check here in the while loop. So then we have the next node. So then we say, okay, does the next node's data equal the data that we're passing in that we're trying to find? If they are equal to each other, then we return that node because that's the one that we like and that's the one that we want to find, so therefore we found it. And it just keeps on going until there are no more nodes that are left in the list, and if that's the case and we didn't find one, then we return null because we haven't found anything. Okay? So for now, I'm just going to say return null for my delete method so that I can test. First, I want to retest my add method because I've changed it. So let me say debug as, it's going to switch perspective on me. Hover over the list. Hopefully the head is 15, which it is. The tail is 10, which it is. Next is 16, next is 10, and then we have a null, so that's fantastic. That is exactly what we want. So that's great. That still works. And there's one tweak that I'm going to do also, and that's in the node class. I want to override the toString method because I want it to show me something more meaningful than just the object location in memory. I'm going to return the actual data for the node. And I think I need to cast it. So I'm doing a cast here. That's what I'm casting it to a string. Because when you have a string and you append an int, it casts it to a string. So that's kind of what my little shortcut here is doing. Because if I don't have this, then you see it has an underline and it says type mismatch cannot convert from int to string. So I just do that to actually convert it to a string. And that way, if I go back and rerun my code in debug mode, now when I hover over the list and say head, as soon as I click on head, it shows me 15. Whereas before, it was showing me a memory location, which was annoying. If I click on tail, it shows me 10. If I click on next node, it shows me 16. If I click on next node, it shows me 10. So it's just a little bit easier to read the data that way, okay? Switch back to my other perspective. So now what I want to do is I want to test my finding. Okay, so I want to say list.find, and I want to say 10 to see if I can find element 10. And actually, I'm going to do that for every single element. I'm going to say find 15, find 16, and then I'm going to say find 20, and I'm going to say find 1. All right, so let's see if this actually does anything, and let's do a system out for each one of these. Okay, I'm gonna do a system out just to sort of go through and explain what's going on as it's happening, and I'll say does 10 exist in list? And same thing for this. Boom, 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 boom. Does 15, does 16, does 20, and does 1 exist in the list? All right, now this time I'm just going to run right through it. I'm not going to debug it. And then down here, we have our results. So does 10 exist in the list? And then it returns the number 10, which is perfect because that means it found the number 10. 15, it finds it. 16, it finds it. 20, it says null, which means it did not find it. And 1, it says null, which means it did not find it. All right, so that's perfect. That's exactly what we want it to actually do. So now what we can do is we can start deleting stuff. Okay, so let's say list.delete, and we want to delete 16. And then let's rerun our code to try to find 16. Okay, in this case, you'll see that doesn't work because we haven't actually implemented the code. So it says, does 16 exist? And then it does exist. I suppose I should have put a little system.print line to say deleting 16. And I can rerun this. And it says deleting 16, and 16 does still exist, so clearly our delete code does not work. So we go back, and we need to implement our delete code. But remember, we want to delete first by finding. Okay, so we need to say find data, which will give us a new node. So we'll just call it node. So we need to find the node. And then we can say if node is not equal to null, then we actually perform a delete. Otherwise, we just return null because we didn't find the node, so therefore we can't delete it. So we can't delete a node that we can't find. So now what do we do? We need to actually, so we found the node. So let's say it says find 10, it goes through and it finds it. We have a reference to the node. So now we need to actually delete this node from the list. So how do we do that? Let's think about that. In the case of node 10, it's at the tail of the list. So there's a few more scenarios to think about. So scenario 3, delete element at tail. Scenario 4, delete element, let's say, at head. And scenario 5, delete element in middle of list. So how do we accomplish these tasks now? Let's see. So we need to figure out, so in this case, if we were to pass in node 10, we can check and see if tail is equal to node, right? If the node that we're looking at is the actual tail of the list, then what do we do? Well, we would need to say, okay, the node before this one needs to be assigned the pointer of tail, and this node's next reference, so this reference, needs to be cut. So how do we do that? So this is a bit more tricky because we don't have a previous pointer. So now we need to think about this. If we are deleting, it would be a lot easier if we had a pointer which pointed back to the node before the one that we are actually trying to delete, right? So that would be one way to go if you were implementing this code. If you are not supposed to implement a previous pointer, then how would you actually delete this node? So essentially what we'd have to do is we'd have to iterate through the list, finding the actual element before we found number 10. So how can we do that? I think we'd have to, well, there's a few ways to do it. How I would do it is I'd probably implement a method that kept track of the node just before the node I was searching for. So I might create a different find method. So I might do, find node before this one, before data. So maybe that's what I would do. And I would say, okay, I'd sort of copy the same sort of find code. But let's see what I would do. If I'm finding the node before, well, again, if the head is null and there's nothing we can do, if the first element is a match, then there is essentially nothing we can do there either, because there's only one element in the list. So I guess that would sort of affect it in this way. We could essentially say if the size of this list is equal to 0, then return null. And if the size of this list is equal to 1, then we just, well, then we have to delete the head, right? So the head is equal to null. So what we would do is we would say, we would create a node to return equals null. And we would say node to return equals head. We would say that the head is null, and we would also say that the tail is null, right? Because, you know, we would want to make sure that we keep everything in what's the word I'm looking for? In sync here. We need to make sure that the head and the tail are kept up to date, because there's nothing left in this particular array, or linked list, I should say. So here we have a size. And you see I've written this down, but it doesn't exist. I want to create it. Int size equals 0. So when we create this array, the size has to be 0. As we add an element into the array, whether it goes to the tail or not, we need to increment size. And if we delete an element, here, in this case where we have nothing in there, then we don't need to decrement the size variable. But In this case, we have deleted one, so we need to say size minus minus. And in this case, we have found a node, so we also need to say size minus minus after we've deleted it. Okay? And finding will not affect the size of the actual array. So now, let's see here. Does this change what I was talking about? Find node before. If the head is null, then return null. If there's only one element in the list, or rather we are trying to delete the element at the head of the list, then, well, I guess that's what happens here. If size equals 1, actually, no, that's not what's happening here. That's if the size is 1. That doesn't handle the case that the size is 10 or more, and we are trying to delete the first element from the linked list. That will not go into this code here. So if we're trying to, so now that the situation I'm trying to tackle is we have a linked list with many elements in it, and we're trying to delete the first element. What do we do? Because we need to find the node before the node that we want to delete. In this case, since the node we want to delete is at the head of the list, what do we do? So, let's see. I'm still not exactly clear on what I can do. I guess one thing we can think about here is the situations in which we'll actually go into the find node before code. So I would never go into the find node, because this is where I'm actually going to implement this method, right? This is going to become find node before. And I'm never going to go in here if the size is equal to 0. Because if the size equals 0, then we're going to return null, and we're never going to hit this code. Therefore, here, this situation where the head is null will never happen. Because if the head is null, the list, or yeah, the linked list is empty, which won't happen because we will have hit this code first. So that means that this code is essentially irrelevant. So therefore, what we can do is if we can say that if the first element is the match, then we can return null, and null will mean something special. Null will mean the element before the one we want to delete is outside of the list, which means the element we want to delete is at the head of the list. All right, so that's sort of what null will represent here. So maybe we should make note of that and say if this method returns null, it means that the element we want to delete is at the head of the linked list. So that means that we need to think of something else in terms of, if we don't find anything. So if we don't find anything with this code, what should it return? So maybe this isn't a very good representation, because usually when we haven't found anything, we return null. So maybe this is not good. Maybe we should say if this method returns an empty node, it means that the element we want to delete is at the head of the linked list. So we can do this, new node with nothing inside of it. Now, obviously there's a problem here because we haven't declared a constructor that doesn't take any arguments. So what we can do is we can create the constructor. I'm just going to click here. I'm just going to create a default constructor with nothing inside of it. That's all that needs to happen. So what that'll do is that'll create a node, but it will not put any data into the actual int data here. Although there's a special case when we say int data with an instance variable, it's going to initialize it as 0. So maybe that's not a good representation of what's going on. But anyway, in any case, 0 will be a special case that we'll need to think about, or that you can think about when you implement this code, because obviously I can't do the whole thing for you. So let's just do that. We'll return a new node. There we go. So now we can assign the iterator node, and we can say while next node is not equal to null. And what we can do here is we can say if node.nextNode.data is equal to data, then we return node. Otherwise, we increment. We say node equals next node. So you see what I've done there? I'm checking to see the next node. So first we handle the case of the first element. The first element is where the head, the first element equals the element we want, okay? The next thing that we handle is the next element in the list. So we say if the next node, if there is a next node, then we check that next node's data. We check the next node's data to see if it equals the data, the one that we're actually checking for, right? So if the next node is the one that is a match, since we want to find the node before our match, then we return the current node. See what I've done? If the next node is the one we want, we return the current node. Otherwise, we increment. Okay, so we say node equals node.nextNode, which, iterates through the list itself. If you've never seen this notation before, I don't have any brackets. It's the same as doing this. And I can get a little bit confusing if I don't explicitly put the brackets in here. But if you don't have any brackets, then it's just going to execute this if statement with just the next line of code, and that's it. And then this line is not part of the if statement above, which is how the sort of the code nesting sort of gives that away as to how this will function. But anyway, that's just an aside. So returns, I'll just be complete here, returns null if there is no match, and returns a populated node if it found a match. Fair enough. So now, why is node to return not being used? Oh, we need to say return node to return. Sorry, I'm just sort of filling that in. This is in the case when the size is, so when we're deleting, and the size is 1, we just need to delete that first one, and we need to return the node that we actually just deleted. So I just had forgotten to put the return statement in there. That's a special case. Now we hit the rest of the cases. So we want to, we found the node before the actual node that we want to delete. So now what is it that we need to do? Well, think about it. If we want to delete node 10, and node 10 is at the tail, so I guess we're talking about this code, what do we need to do? Well, we need to say, get the previous node, and delete its pointer, and assign the tail to be here, because we need to keep the tail updated, as well as obviously decrement the size. So here we go. If the tail is equal to the node that we want to delete, so sorry, there's a bug here. You see the bug now? This node has changed. This is now the node before the node we want to delete. So remember, there's a few cases here. If the node.data, I want to say is empty, but I can't because it's an int, and that's a special case, which I don't want to get into. If the node's data is 0, then that means that we need to case where we need to delete the head. All right. So we can sort of figure out that code. Else if the node does not equal null. So this is the case where, I don't know, we found a match, right? That we need to delete. This is just where we need to actually delete the actual node. But here, the node, not equal to null, this node represents the node before the one that we want to delete. So that's important to remember. So here we want to say if the tail, so back to deleting this one, if the tail's data is equal to data. Data is the one we want to delete. Don't forget that. If the tail's data is equal to data, then that means we need to delete the tail, right? So how do we do that? Well, we need to say node. I guess I should rename this variable. This should say node before How can we name it? Node to delete. That's a very long name for variable name, but I'm being explicit here. This is the node before the node we want to delete. So we want to say the node before the node to delete dot next equals null, because we want to delete the reference for this one. We want to delete it. And we want to say tail is now equal to the node before the node to delete. Does that make sense? Because we've updated the tail to point to 16, and we've obliterated the pointer for 16 to the next node. So that's if the tail is the one we want to delete, then we can do that. Otherwise, let's see. Although I'm realizing this didn't need, oh yes, it did, never mind. I was going to say this didn't need any searching, but yes, we did need to search to find the node before the one we wanted to delete. In the other cases where we just have a node like here, and we just want to delete it. So what do we need to do? Well, we need to say node 15, the pointer for node 15 now needs to point to not 16, it needs to point to 10, and I believe that's it. I believe that will essentially obliterate node 16. So, darn, because now we need to find, oh no, that works. So we need to say node before the node we want to delete. So in this case, we want to delete node 16, so we find node 15. And then we want to say dot next node is equal to, and how do we do this? We would need to say node before node we want to delete dot next node. I think we can just iterate it through twice, right? So that way we say node before we want to delete. That means node 15. The next node, so the pointer, should point to 15.nextNode.nextNode. So 15.nextNode.nextNode is 10. So we're saying 15's next should point to 10, which is exactly what we want to do. So I believe that's what we would need to do to delete that middle node there, node 16. And then the only case we need to have left to figure out is the head situation. So what happens if we wanted to delete node 15? How do we do it? Well, if we want to delete node 15, then we would just say that the head is now equal to the next node. That's it. So, let's see. We would say head is equal to head.nextNode, right? Because the head points to here. We want to say that this head now should point to the next node from the beginning, which is head.next. Make sense? And since we did that, we also want to say size minus minus because we want to make sure that we keep our size of our linked list up to date. Now, there we go. A lot of code. I'm not exactly sure if this is going to work perfectly, but hey, we will see. So let's go to our linked list test. Let's rerun this code. And there we go. So now deleting 16, does 16 exist in the list? No, it doesn't. Interesting. So it looks like it might be working. But the best way to see if this is working is to be able to iterate through the actual array and print out its contents. So let's create a very quick method, or let's create a method very quickly to say, let's see. Let's just say traverse. This will just be, actually let's not make this a public method, let's just make this a protected method because it doesn't really make sense for everyone to execute this method. So we'll just say traverse, and what this will do is it will say while, first it'll say if head is not equal to null, then it will traverse through the list and say while node equals head, node dot has, oops, dot next node is not equal to null. So we will say sys out node, and then we'll say node equals node dot next node, and sysout node. So we'll print out the first node, which is the head, then we'll increment to the next one and print it out, and check and make sure that there's another next one, and then increment and print it out. I believe that will work properly. Obviously, we can test this out by doing this. We'll say list.traverse, and then we'll say list.traverse. So after we've added everything, and we'll traverse it, and then after we've deleted 16, we will traverse it. So let's run our code. So 15, 16, 10. Does that make sense? Yes, because we have 15, 16, 10. Does it exist? Yes, yes, yes. These two do not exist. Very good. Deleting 16, now we have 15, 10, which makes sense because we deleted 16 from the middle. Fantastic. So now, let's say list.delete the tail, which will be 10, right? Because 10 is right here. Sorry, 10 is right here. So we will delete the tail, and then we'll do another traverse. And then we'll say list.delete, and we'll delete the head, and we'll do list.traverse. Let's see what happens. Oh, that's going to be tricky because we didn't put out deleting. Let me do my print deleting 10 and deleting 15. Let me rerun that code. Okay, so deleting 16, we have 15, 10. Deleting 10, we have 15. Deleting 15, we have nothing. So it looks like our code is working nicely with adding and with deleting and with finding and even doing a little bit of a printing of the list. If we want to, we can add, more elements to sort of make this list a little bit more impressive. We can say 30, 50, 82, and 100 or something like that. And we can run. Boom. So here we say deleting 16, so you see 16 no longer exists where it previously did exist. Now it does not. Then we say deleting 10. When 10 was at the head of the list? No. 15, 10, 20. So 15, 20. You got rid of 10. And we want to say deleting 15, which is at the head. And there we go. And I think everything looks okay. The only thing I can think of is to output the size of the actual linked list, but I don't want to get too far into those nitty-gritty details because this video is also already gone on for quite a bit of time. Hopefully that helps the original person who has asked the question about their homework assignment for implementing a linked list, as well as anyone else who in the history of programming needs to implement their own linked list. I know I had to do this back when I was in university, so hopefully this helps you out as well. So there you go. If you love this actual video, if you love the idea of getting help on your homework like I've done, I would strongly suggest that you check out coderscampus.com. All right, bye for now.